Ever wondered how an AI system makes predictions or conclusions from data? This process, my friends, is what we call AI inference. It's the backbone of how AI systems decipher, understand, and draw conclusions from the data they're fed. In the vast world of AI, there are many ways to perform inference. Today, we're going to focus on a particular method, one that's as intriguing as it sounds: inference through sampling. Now, what's this, you ask? It's a technique used in probabilistic graphical models, a subset of AI, to estimate complex probabilities that are too intricate to solve exactly. In simpler terms, instead of trying to compute the exact outcome, we generate samples from the distribution and then use these samples to make an educated guess. It's a bit like throwing darts at a target in the dark, but with a sophisticated mathematical torch guiding your hand. In the next few minutes, we'll uncover the mystery behind inference through sampling. Are you ready to dive into the world of inference through sampling? Buckle up, because this journey will lead us to the heart of many AI applications. Imagine a mystery box filled with balls of different colors. You don't know the exact distribution of colors inside the box. However, by taking a handful of balls out, you can get an idea of the color distribution. This is the essence of sampling. Now apply this concept to AI. The mystery box becomes a complex model, and the balls are data points. We don't know the exact distribution of data points in the model, but we can sample a subset of data points to get an approximation. Inference through sampling is a method we use to estimate complex probabilistic queries that may be too computationally heavy to solve exactly. What we do is approximate the posterior distribution by generating samples from said distribution. Picture an iterative process that begins with an initial assignment of values to all variables. We then select a variable to update, sample a new value for it, and then update the variable with the new sample. This process is repeated until we reach a point of convergence. Now, reaching convergence doesn't mean we've hit the jackpot and discovered the exact distribution. Instead, it means that after a large number of iterations, the samples generated should approximate the true posterior distribution. Once we've generated enough samples, we can use them to estimate the posterior distribution and compute the desired probabilistic queries. While this method can be computationally expensive, it's often used when exact inference is not feasible due to the complexity of the model or the size of the data. In essence, inference through sampling offers a trade-off between accuracy and computational cost, allowing us to estimate approximate solutions to complex inference problems. So, inference through sampling is all about approximating complex models using a manageable number of samples. Let's explore a popular method used for inference through sampling: Markov chain Monte Carlo, or MCMC. Picture it as a journey where you need to reach a destination, but the path isn't clear. The journey starts with an initialization, where you randomly pick a starting point. From there, you begin iterative sampling, which is like taking steps in different directions. In each step, you select a variable to update, sample a new value based on the current values of other variables and the probability distribution, and update the variable with this new sample. After taking a large number of steps, you reach a point of convergence. This is when the steps you're taking start to form a pattern that mirrors the true posterior distribution. The final stage is estimation, where you use the pattern formed by your steps to estimate the posterior distribution and compute the probabilistic queries. And that's a quick overview of MCMC, a widely used method for inference through sampling. Now that we've explored inference through sampling, let's summarize what we've learned. Inference through sampling is a fundamental technique in AI, specifically in probabilistic graphical models. It's used to estimate complex probabilistic queries that are computationally challenging to solve with precision. Instead of calculating the exact posterior distribution, we approximate it by generating samples from the distribution. A popular sampling method is Markov chain Monte Carlo, or MCMC. This method involves an initial assignment of values, iterative sampling until convergence, and finally estimation using the generated samples. Although these methods can be computationally demanding, they offer a balance between accuracy and computational cost. They're an invaluable asset when exact inference is out of reach due to the complexity of the model or the size of the data. Remember, inference through sampling is a powerful tool in AI's toolkit, helping to turn complex data into actionable insights.